Good morning, everyone. Today is April 4th, 2020, and this is the John Chappell Natural Philosophy Society Science Chat. So welcome, everyone. I see today we have John Kirian. Let's see here. Let's add him on stream here. Right. Can you hear me, John?
I hear you fine. You hear me?
Okay, I'm hearing you fine. So you had sent me some information about the Big Bang.
Right.
So would you like to share that? You can share your screen if you'd like.
Okay, is that the best way to do it? How do I show the slides? This is a new computer here for me. This is my wife's computer. I don't usually use it, so.
Okay. Well, you're coming in good. It looks like she's got good equipment. The way you share is that there's a button down on the bottom of your screen. It says share screen, should be about in the middle. And what you do is that first you show your slides on your screen so you can see them.
Okay, so what I have to bring them up on this computer, I take it, right?
Yes, you need to bring it up on your computer.
Okay, should I click the shared screen first or not?
No, we'll do that second.
Okay, good. Okay, the thing popped up. It said screen sharing tips. Okay, I guess I need to minimize this picture. Unfortunately, I don't have a mouse here. I'm just using my finger, so it might take a little bit.
Yeah, I wouldn't worry about minimizing things too much because you're still going to have to access the screen that's got the share screen button on it first.
Okay.
Just get it up there somewhere.
Okay, let me see if I can find my, where am I here? Pretty sure I put these slides on this computer. Got a different website here. Let me close this one.
Now you did try sharing those slides with me. Well, it looks like he managed to kick himself off. So he did manage. He tried to share the slides with me, but it required some authorization or something. But let me see whether I can go and retrieve at least his website, because he does have a website. So let me go and hopefully he'll figure out he has to get back in here. Let's see here. Okay. So we'll just start off with that, I think. He seems to be a Big Bang, critical of the Big Bang theory. Today we have Bill Lucas and Ian and Roger and Carl and James. So today's topic is going to be about the Big Bang. So I was wondering, do any of you guys have any particular feelings about whether the Big Bang is true or false, or what do you guys think about the Big Bang?
I've done some work in that area, and I have derived the force of gravity from the electrodynamics, and gravity in that approach is based on the force between vibrating neutral electric multipoles, such as dipoles, quadrupoles, and octopoles. And these multipoles, besides giving rise to the force of gravity, are also slowly decaying. And the decay of that generates the cosmic background radiation, which is supposedly the origin from the Big Bang. But since we're able to predict it directly from electrodynamics, with no theory of gravity, it looks like it may be just the decay of gravity. And decay of gravity causes the gravitational field of the Earth to get weaker, which causes the Earth to expand. And we see the evidence for that expansion in the expansion stretch marks in the bottom of the ocean. And also,
so you're basically attacking the CMBR data, right? Since you can explain it a different way, right? So no
that's
big
right.
bang necessary.
But they have a problem with it because you see the the age of the universe that they're using, excuse me, is many billions of years, like 13 or 16 billion years. But our measurements of the age by radioactive decay show that the 16 known methods for measuring the age of the Earth all now agree that it's 10,000 years or less. And so that data is going to falsify the Big Bang, because Big Bang is much longer time ago, and it doesn't seem to be any evidence for things occurring in that time frame.
Well, I thought that the latest, like, they do like lead decay change or whatnot, as they say that age of the Earth is 4 billion. So how are you saying that they're agreeing that they're less than 10,000 years?
Well, they take, for instance, the decay of uranium. They'll take a mineral that has uranium in it and lead. They make the assumption that the Earth was very old before that mineral formed, and all of the other radioactive isotopes that could decay to lead had already decayed before the mineral formed. And so they could attribute all of the lead to the decay of uranium. And when they look at that mineral, they find there's about the same amount of lead as there is uranium. And that's how they get the age of billions of years for the Earth. But with the discovery of radio halos, we can see what it was that decayed to lead in a particular mineral. And so if we take a mineral that has some uranium and lead, and we look under a microscope with it, we see other isotopes decaying to lead. And so when we take those into account, the age of the Earth drops from billions of years to 10,000 years. And all of the radioactive decay methods are in agreement with that. But the old age of the Earth, there's a number of radioactive decay methods that do not agree with that age and never have. And so, anyway, the only way it appears to make all of the data consistent is to properly take into account the radio halo patterns that show what happened when something decayed. What a radio halo pattern is, if I have a mineral with something that's decaying, let's say it's uranium, as it decays on the way to forming lead, it gives off alpha particles. These alpha particles have a certain amount of energy, and they what they do is they modify the medium as they go through it and make a pattern. And the pattern is that it goes a certain distance, and then the alpha particle gets absorbed in the nucleus. And the distance it goes is a function of the energy the alpha particle is getting when it decays from the original isotope. And so you see a number of rings about a small crystal of, say, uranium or some other material. And you can see from the number of these halo patterns that are etched into the mineral, you can see what it was that was decaying. So when we look at these minerals, we see all kinds of, I think we see about 40 minerals, 40 radioactive isotopes in uranium minerals that decayed, and those are the original isotopes there. They're not secondary. And So we're able to see what the true age is. But once scientists discovered that, they did not want to take it into account. And so they ignored it. And the work was done, believe it or not, at in Oak Ridge, Tennessee, at the laboratory there, the government runs for all kinds of radioactive tests.
Okay, so we have one piece of evidence there that the age of the Earth is not the billions of years that the Big Bang Theory would suggest.
No, we have 16 radioactive decay methods for measuring the age of the Earth that all agree. Before the discovery of radio halos, only 3 of the radioactive decay methods gave an old age. The other 13 have always given a young age, and they were ignored. And so that's what's
the age of the Earth, right? So it could be that the universe could still be 16 billion years old, but the Earth is only 10,000 years old.
Yes, something like that.
Well, let's see. We've got John back here, so let's see whether he can get back and see if we can get him to share the screen here. So, you able to share the screen?
Yes. Hi. I'm here.
Okay, so let's see if we can do screen sharing here. So there's a button in the middle there. It says share screen. Now you click that once, and then it says screen sharing tips, and then you have to click share screen button again, and then you'll get a share your screen dialog. And on the left-hand side, it says your entire screen. You actually have to click in the middle of that screen to select that, and then click on the share button.
Okay, I click shared screen. Click share screen again.
Yep.
Okay.
Then click on the picture of your screen.
Okay.
And then click share on the bottom. Let's see if that works.
Share here. Okay. Oops. Got it. Come on. Click.
Click the share button. That's the last step. After clicking on the picture of your screen.
Oh, click on the picture of my screen. Okay.
Yeah, there's the picture of your screen there.
Not highlighted. All right, got it.
There you go. Now I can add your screen. So now we can see your screen, and now you want to put up your slides.
Okay. So now I got to go find my slides, right?
Yep. Find your slides.
Guess I'll get a new tab up here. So where did it go? Where did it go? I'm sorry for holding you guys up here. Let's see here. Here's probably this. Okay, got it. There, you got it?
There we go. We can see that now. Yes, we can see your slides here, gravity and the redshift, why the Big Bang is wrong. You can go full screen on that if you want.
Okay, good. What do I have to do here to share? You want me to share it or just leave it up?
Just leave it up. We can see it already.
Okay, good.
You can go into slideshow mode if you want. That will fill the screen, and you can proceed that way.
Okay, well, we'll see. I want to talk a little bit about this. The Big Bang, of course, was first said by Fred Hoyle at a BBC thing, and it was a joke. And but Fred almost had the right idea of what the universe was. He early on in his papers, he said that light was being converted to mass, and later on, he didn't really make that statement, but when he did that, he came up with the universe, but he still had the redshift being due to the Doppler effect. So there was a great Big Bang at the beginning and everything was flying apart. But if he had really just shown that the process where the light converts to mass is forms of a redshift, it would have solved everything. Now I've got a website here, this one here, which has got over 500,000 hits on it, and that covers most of the stuff that we're talking about here. But I want to talk pretty much about gravity in this speech here, and let's see if I can bring up. I don't know how to bring up the next slide. Let's see, would this do it? Maybe. No. Let's see.
Usually this is PowerPoint. If you press F5, that'll put you to slideshow mode, and then I think just like page down.
It's a PDF. So my son-in-law put it in PDF mode. So.
Oh, it's PDF. Then just clicking in that right where you're at, that should get you to the next page, I think. You're clicking there, and that's not getting you there.
Oh, there we go. Okay, good. That's it. Okay, good. Oh, the first slide I hear back in the 1800s, there was a book published and it was called Kinetic Theories of Gravity, and it included the whole history of the theories of gravity way back to Newton's assistant Fabio and the Swiss physicist Lesage. They all were pushing theories of gravity, and gravity was thought to be a push from the outside by ultra-mundane particles. And Brush must have read this book because he published his theory of gravity, and he called it a kinetic theory of gravity, which is the same thing. Brush built this big windmill you see here in this picture. Give you an idea how big that is. This little, I don't know if you can see my cursor or not, but oops, let's see here.
Yeah, we can see that flitting around there.
The little guy down here, right down here where my cursor was, is that's a man down there mowing the yard. So this is a big 6-story tall built thing, and used it to power his mansion that he had on Millionaires Row in Euclid, Ohio. And he had a generator. Brush was a multimillionaire, and the way he made his money was when he was a kid, he would fool around with electricity, and he was making sparks, and he made his own generator using fence wire. He was the youngest of 9 kids, and lived out in the farm country in Ohio. And he built a generator and had the horse pull the generator around the fields in order to, so really hard, it was a horsepower generator. He went to college at the University of Michigan, got a degree in geology, and then, but because he was always interested in electricity, he hooked up with a friend of his, and he invented the arc lamp, and he introduced street lighting to the world, and he made Broadway become a great white way. First he lit up Cleveland, and then he became a very remarkable person in that he his company eventually merged with the Edison company to become General Electric, and so he was one of the founders of General Electric. He also made a bunch of batteries, and his battery company became Union Carbide and made ever-ready batteries. And lucky for me, because I got a Union Carbide scholarship. So thank you, Mr. Brush, for that. And I got a couple of summer jobs out of it right in Ohio, very close to where his research labs were. And he also was the first president of the Linde Air Products Company for America. And which squeeze down air to make liquid hydrogen and oxygen and liquid air. And he also formed a mining company, and he made big beryllium mine. Now let's see if I can get to the next slide here. And this is a picture of the James Webb Telescope. So the brush, a lot of the brush companies are still in existence, even though most of them got absorbed into Union Carbide and General Electric. But there's still a brush company in England where they make generators all over the world. And the mirror that you see there is a multi-sectional mirror, is a beryllium mirror, and the beryllium comes from the brush mine. So there's a big connection with today, and the Brush-Wellman Beryllium Company is now called Materion. It's a new thing, and so he published this paper in 1910 that called it the kinetic theory of gravity. And he said that gravity was a push from the outside of real long wavelength electromagnetic radiation. It turns out that Crookes, who was the British chemist, had been doing some work with what do you call it? Quantum chemistry. He was measuring chemical reactions very precisely, and the sunlight shone on it, and the weights suddenly increased. And so he was that was his sort of the kinetic theory, that he said light had something to do with gravity. And then Brush came up with the idea that real long wavelength light would be pushing everything together, and that agrees 100% with what I'm thinking nowadays is really what gravity is. There's a book called Pushing Gravity. I have a paper in it that sort of describes that. Okay, let's go to the next. What did I do here? Help. Wrong thing. Let me close this. I'm back. Let's go back here. Next slide. Okay. Let's go back up one. Okay, yeah, let's go to Hubble. So Hubble, of course, was he was a lawyer who was coaching high school basketball, and his 8th grade teacher had really got him interested in astronomy. So he went back to school and got an astronomy degree, and then he ended up being the guy who measured the redshift in the galaxies and saw that I don't know what this thing's popped up here for. Is that really, I don't know. Okay, and so he came up with a famous law that says, hey, the redshift is proportional to the distance, and eventually a lot of people who thought those redshifts were Doppler led to the idea of the Big Bang. But he did not believe that the redshift was Doppler. He believed it was a new principle of nature. And so his papers and everything he said disagreed with it. And anyway, everybody's pretty much familiar with what the idea is. Okay, next slide here. Boom. Here's Grote Reber. He's also from Wheaton, Illinois, same place as Hubble. And what's interesting is Grote Reber's mother, Harriet Grote, was Hubble's 8th grade teacher, and his mother was the one who discovered, got him all interested in astronomy. And Grote made the first radio telescope, made the first radio maps of the night sky. And when he was with the National Bureau of Standards, he got them to in the 1940s to look at the sun and measure the radio output of the sun using this Würzburg antenna. Grote and I became really good friends, and we scrambled around Boulder, where I live, and looked for this antenna. We found it, and it was such a remarkable thing. This antenna was first set up in Dulles Airport in Washington, D.C., and then they moved it to Boulder, Colorado when Bureau of Standards moved to Boulder. And it was set up really close to our house in the suburbs of Boulder. And Grote and I scrambled around and we found it. Grote and I became good friends, and I'll tell you why we became good friends here. Let's see, next slide. Grote built this thing. It doesn't show up real well here, but all these little white poles they look pretty little there, but they're actually 70 feet tall. They're taller than that windmill that Rush had. Huge, big array. This is the biggest astronomical single instrument ever built in the world. It's 220 acres, and the reason he built it was he had decided that radio astronomy was in pretty good hands after he'd invented it and spread it around, made these antennas, made measurements of the sun. It also helped John Ert in University of Leiden make maps of the night sky, and using the same Würzburg antennas that he was using to look at the sun, and he had that all set up. And this big antenna here he decided he wanted to go look at parts of the spectrum that nobody else looked at. And these are, this says 100-meter radio telescope, but actually he's measuring it in wavelengths up to 500 meters long, half a kilometer long wavelengths. And in order to do that, he had to not only build this antenna, he had to wait for the ionosphere to open up. And that happened only during solar minimums at night in the wintertime. And he had this all built in Tasmania because he searched the world and he found that that was the place where this was done. So Grote was a very inventive guy. Like I say, I became good friends with him. He spent a couple of nights with him at my house. And he had some results from having made these measurements. And let's see here, I should have pictures of the results. I hope you can see that. This is maps that he made, and this shows what the night sky looked like in the southern hemisphere from Tasmania using this antenna. And you can see it's got a whole bunch of squiggles, and these are lines of constant intensity. So where there's concentrations, there's big concentrations, and this is where the big concentrations are. That's the Large Magellanic Cloud, and he's able to identify the small and large Magellanic Clouds in other places in the sky to correlate with them. And this is an incredibly unique result. And what's really unique about it is that these lines continence brightness, where the concentrations are not bright spots like you would see, they're dark spots. And so this is like a well. So what's happening is the really long wavelength stuff is blocking out the galaxies in front of it are blocking it out, and so the wavelengths it's a bright sky with dark things. Unlike the microwave radiation, which is at 2.5 degrees Kelvin background, dark background. He says that the corresponding measurement in this thing of the temperature of the general background is 1,000,000 degrees. So here we have a very bright background, and this is the bright background that I think Brush was looking for to push everything together to cause gravity, which is a very interesting idea. To cause gravity, is a whole new way of looking at things. And what's his name? Feynman, in his talk, he used to say that, hey, people come along and they discover, hey, you can get an inverse square law just like gravity, and if the amount of the mass is, if you measure mass by how much it absorbs the light, then the shadow it casts, it winds up pushing them together. Of course, G equals M1, M2 over R squared. He says, everybody gets excited about it. He says, but that would never work because satellites going around the Earth would run into this background stuff and it would cause it to slow down and it would crash. Well, Feynman hadn't been thinking of real long wavelength electromagnetic radiation, and that doesn't really become effective until you approach the speed of light. And so what actually happens is as you approach the speed of light, and that means that the mass gets slowed down. It acts like it's getting heavier. It's exactly what the theory of relativity says. So this idea is consistent with the theory of relativity. Following what Grote did, we come across quasars, and this is Martin Schmidt, who was one of Jan Ort's students at University of Leiden, the same place where Grote had given these things, and they found this quasar. Here's 3C273. That was the first one found, and it's a bright radio source, and it has a huge red shift, and it just looks like a star. And so they call it a quasi-star, or quasar for short. But it can't be, they think, because it has a big red shift, it has to be super distant. But the red shift is due to the Compton effect, which is, or it's an intrinsic red shift. It means that the object is associated with the object itself. If the star has a whole bunch of electrons around it, the light will come through, it'll hit the electrons, it'll transmit energy to the electrons, and it'll be red shifted, and it'll be what's called an intrinsic red shift. It's just associated with that source. It has nothing to do with the distance it is. It's unlike the other red shift that Hubble was looking at. It said, hey, the further away it is, the bigger red shift it has. So red shift is not necessarily a measure of distance if there's a big intrinsic red shift going on here. Let's see, which order do I have this in? Did I miss this slide? Okay. Well, Margaret Burbidge is one of my heroes. She's 100 years old still. She's still alive. She and her husband wrote the book on quasars, and she's got a whole line of things that she did. She was the only director of the Greenwich Observatory not to be called the Royal Astronomer. But she's convinced that the quasar redshift is intrinsic. and not Doppler. And one of her people that she agrees with is Halton Art. Chip Art and I've spent a whole afternoon with Chip and talked about the redshift being caused by the Compton effect. And he likes to show pictures of objects that have two different redshifts, but they're physically connected. And he and her were good buddies here. Let me go back a little bit. I think I may have missed a slide here. I guess not. I don't know. Okay. Little mechanism problems here. Let's go down another one. Okay. Now there's also a redshift on the sun. And I wrote a paper in association with my good friend Brooke Sharp, and we showed that the redshift on the sun varies between the center of the sun and the edge of the sun. So if you look at the edge of the sun, obviously you're looking through a thicker part of the solar atmosphere, and there's more electrons there. And we showed that there's a correlation between the distance the light travels through the electrons in the solar atmosphere agrees with the redshift on the sun. And it turns out that Compton himself had also said that the Compton effect caused it. And there's sort of what's interesting about that is that this redshift is bigger than any gravitational redshift that other people think would happen out at the limb. And whenever there's a solar flare, there's huge redshifts inside the solar flares that nobody's able to explain. There's a satellite I happen to have worked on called R-HESI, the Rubin High Energy Solar Instrument. And it showed that the heavier elements, which were the ones, the magnesiums and the all had bigger redshifts than the lighter elements, which they also have, which means they have different electrons. So what happens during a solar flare is the high energy ionizes these elements, and the light bounces off by the Compton effect, and this agrees with the same sort of thing that we see in quasars. So we see it in the sun. So the question is the redshift due to the Compton effect instead of the Doppler effect? If it is, then just means that there's free electrons spread out, or ionized hydrogen spread out throughout the universe. As light travels through it, the further you go, the bigger the redshift. And the redshift is due to the Compton effect, which means that the light is bouncing off of the electrons, and the wave front is being reconstructed, but it's losing energy to the electrons. And so the electrons are picking up this energy, and this shows that the universe is not expanding. The other thing it does is this not only explains the quasars, but it also is the thing. There's a problem associated with a static universe, and that's whether or not it's stable or not. And that is Tolman, who's was Hubble's theoretician at Caltech. He did an analysis where he looked at a Einstein static universe, and he tried to measure the distance around it. And he made the calculations, and he said, okay, let's shoot a test particle off and allow it to go in free fall, responding to gravity and to radiation pressure. And when he did that, what Tolman found was that the distance that it went around depended on the total amount of radiation pressure and the total amount of gravity that there was in a stable static universe like that, and it wouldn't be stable. If the stars are radiating energy, then they're losing gravity. It's converting mass into light. Then that would cause the radius to change, and if radiation pressure was causing the lights to if light was being converted into mass somehow, then the radius would change. So it turned out that the stability of this was such that if the thing that we observe all the time, which is like the sun shining and stars shining, which would be converting mass into light, that would cause the universe to contract instead of to expand. But now we have the Compton effect going on here, and the Compton effect is pretty interesting because if you look at an electron at the Compton effect from the standpoint of the electron, it sees light coming from all directions, and it can't increase in velocity because the velocities cancel out, and so it sits there and absorbs the light energy, producing the red shift, but it has to get heavier because E equals mc squared. If it's observing energy, not increasing in velocity, it has to increase in mass. So we get the situation where we can make those two things cancel out, and that makes the universe stable. But it would be filled with long wavelength radiation, and gravity turns out to be the radiation pressure. Now, there's Olbers Paradox that we have to worry about. Before there was people discovered the red shift, the night sky was covered with stars, and if you looked out, the further you looked out, the bigger the volume you're seeing, and so the number of sources you see would increase as the cube of the distance because the volume increases as the cube. But the energy would only fall off by the inverse square. So this would mean that the night sky should actually have an infinite amount of energy coming from it. But it doesn't, obviously. It's dark. The night sky is dark, and that's Olbers Paradox. Why is it dark? There are theories. There's a tired light theory floating around here that says that light as it gets tired, it gets a red shift. This would still be infinite amount of energy there because each photon would lose energy. So if you went out to the distance where the red shift is 1, there's a finite volume there and a finite amount of energy that you would get, and you call that E. Then you go out to 2, twice the distance, then you get another E there, and you keep adding E's. But the red shift, if it's tired light, each photon in the second one would have half as much energy as the energy in the first one, and in the third one it would have a third as much energy, and so you'd have an infinite series there. You'd have E times 1 plus a half plus a third plus a fourth plus a fifth. That doesn't converge. That's still an infinite number, but almost all of that energy would be at long wavelengths. So a tired light theory doesn't really work. But there's a steady state theory, which is the one that Hoyle had. This would be a universe that has an infinite universe that has a Doppler effect in it. Well, in Doppler effect, you have a thing called time dilation, and that is if everything is moving away from each other, then the distance that that not only is the light redshifted by the Doppler effect, but the distance between photons is also stretched out. So the number of photons you would receive would be smaller. So you would have, you'd lose a half of the energy due to the redshift, and another half of the energy due to time dilation. So you would have basically a fourth of the energy. So you would have, turns out you would have E times 1 over n squared, which is, turns out to be the Basel problem from Basel, Switzerland. Euclid solved this problem, and he says, hey, E over 1 squared is equal to, the sum of 1 n equal 1 to infinity is like 1/2 plus 1/4 plus 1/9 plus 1/16. That converges to pi squared over 6. What this really says is about almost all of the energy. The first part would be, the energy would be E, and then the sum of all the others would only add up to 0.6 tenths of, or 0.62 tenths approximately of all the rest. So almost all of the energy would come from redshifts less than 1, and you'd have a dark sky, and that solves Olbers paradox. In my theory, which has the Compton effect, the redshift is no time dilation. It's the same as tired light, but I have in order to make the redshift proportional to the wavelength, I have that the size of the redshift is greater for longer wavelength stuff, and as the wavelengths get longer and longer, I get an acceleration of the loss of energy. So although I don't have time dilation, there's still a finite energy with lots of energy at long wavelengths, which is just exactly what Grote was observing. So and that provides the energy to cause the gravitational push, and explains why things are. Here's the redshift, have a magnitude of 11.1, the biggest redshift ever found. This is so bright, it can't possibly be there if the redshift is Doppler. But if it's a Compton effect, it's easy because redshift accelerates, it can be that bright, and it is still there. And that's really shows that we're in agreement with the world here. Let's see, what else do I have here? Boom. So, about to wind this up. I did this one. What did I do? I'm down here. The redshift, just to summarize it here, the redshift, there's free electrons in outer space. Redshift is due to the Compton effect. Explains quasars, Reber's long wavelength observations. Universe is stable, filled with long, and it's due to pressure, to radiation pressure. Now, I didn't talk very much about Mach's principle or anything else, but that kind of winds it up and explains most of everything here. I think this should be about the end of it here. Okay, where am I? I think I left one fun picture here. Oh, this one, yeah. Hey, this is another interesting thing here. If you look at the microwave background, there's the microwave has a big dipole, they call it. It's the 2.7 degree background radiation, and the solar system is moving with respect to this background radiation. And what that does, it means that in the forward direction, there's really bright area, and in the dark other area with the blue area here, there's a darker area. It's and the background people have to subtract this out in order to get to their background, because They want to take away the effect of the solar system moving. It's moving at about, 186 kilometers per second or something like that. It's pretty bright and it's moving at a pretty big speed. What's interesting about that is this forms a dipole. The bright spot is the North Pole and the dark spot is the South Pole, you could say. And then you could make two other poles around the bright spot where it shows where it's a little dimmer on each side. That's called the quadrupole. And then there's the octupole. What's interesting is the quadrupole and the octupole are all lie in a single plane. And it turns out that lines up with the ecliptic plane. And they say that's just a coincidence, but I say that's not a coincidence at all. Because if we're moving with respect to the background radiation, which we see in the microwaves, if we're doing the same thing at the long wavelength stuff that causes gravity, we'll see that over billions of years of the times that the Earth has existed and the solar system's existed, it's been pushing all that debris into that plane, and that's why the external push of gravity causes the ecliptic plane to be like it is, where all of the planets are all aligned and all of the asteroids and everything. So that really gives us real insight as to what's going on here in the world. Let me get down here one more. Nope. What happened? Okay, I'm done.
All right. Thanks, John.
I lost you. Good. Sorry, I was kind of not real great speaker there. I was hesitating and stuff. I should have practiced that a little better. Sorry about that. But anyway, hope I didn't put everybody to sleep.
No, that's very interesting. I mean, I think I followed most of your points there, right up to the point, your last bullet point, which is that gravity is caused by long wavelength radiation, which seemed to be quite a large leap. So how do you
else that? Yeah, but it turns out that's consistent with the idea that of gravity. I mean, it doesn't disagree with all the theories of gravity right now. They're just describing how the force works. There's I didn't get into Jean-Pierre Vijay, but the only problem that seems that there was a Gedanken experiment, they called it, that Einstein thought about, which was if you're in a spaceship that's got the rocket firing and you're moving at 1g force, if the let me see if I can find my picture here, but anyway, if the here I am, if the what was I going to say? Oh, if you fire an arrow at a target on that ship, as the rocket is accelerating, the arrow will fall down. If the rocket is not accelerating, of course, the arrow will go straight. And that is, the arrow will act exactly the same as if it's in gravity. Is the idea that if radiation is a push from the outside, does that, I mean, if gravity is a push from the outside of long wavelength radiation, would that happen with light? If you shone a light beam at the target, would the light beam bend? It's not at all obvious. But Jean-Pierre Vijay, which I happen to have had a session with by some rare chance, that he happened to be at the University of Denver when I was around, he had the idea that the redshift is a Compton effect, but that photons have a little teeny mass. And if the photons had a little teeny mass, there was photon-photon Compton effect shift going on instead of photon to electron. And this would mean that the long wavelength radiation would actually hit the light beam, and it would fall at the same as gravity also. That Gedanken experiment is called the equivalence principle, which means the equivalence of not mass to energy, like some textbooks say, but the equivalence of what I want to say, equivalence of gravitational force and inertial force. So they're the same, whether you're in the inertial force is, of course, the rocket accelerating, and the gravitational force is the gravity. So Jean-Pierre Viget's idea would really solve that problem. It shows how there can be gravitational what do I call focusing? Does gravitational focusing can happen and so forth, which really does. So I'm really of the belief that Jean-Pierre Viget had a really good thing going there with his idea. Jean-Pierre was supposed to be Einstein's assistant. He was to come join him at Princeton, and he couldn't get in the country because Hoover wouldn't give him a visa, because he's, of course, a French communist. But anyway.
Well, I'm thinking that if you have the hypothesis that gravity is caused by low frequency waves, then are there any experiments that would directly show that? For example, we can easily create low frequency waves now with our radio equipment. And could you show that if you filled a room with low frequency waves, that you could see the radiation pressure, perhaps something direct like that?
I'm all for doing that. I agree with you. We'll come up with an anti-gravity machine here somehow.
Somehow.
We definitely understand what gravity is.
That's just kind of the disconnect I'm seeing with the association of the ultra low waves. I mean, because all you've shown is that, yeah, there's lots of low frequency waves, but there's also lots of regular ambient light. There's also, microwaves. It's like there's all kinds of different frequencies. Why would it be the ultra low frequency, which would be the frequency that has the least amount of energy, right? Why can it be?
But the interesting thing about the low frequency waves, if you're in the basement of your house, you can still receive your radio. You can turn your radio on and you can get it. You can't see the light from the radio. It doesn't go through your house. The low frequency stuff, very highly penetrating. The lower it gets, the more it penetrates. It goes right through everything, and it doesn't go through undisturbed, is my thought. So that's why it seems like it's a very low energy thing, but if there's enough of it, and it's very smooth background, and that's why gravity is a nice smooth force. It's continuous force. It's a very subtle force. It's everywhere, and it goes right through the earth. Get down near the center of the earth, it may not be holding things together too well, and so that's maybe why the center of the earth, the material down there, kind of wants to expand a little bit. We may also be creating mass down there also. And of course, I know the people I have a long history here with John Chappell. I don't know if you know that or not. Did I ever tell that to you?
No, I don't think so.
This goes way back to, you want to know the history of where did the John Chappell Society come from? Way back in the 1960s, I found a classified ad in the back of it that said the Association for Pushing Gravity Research was going to have a contest, and they want to have somebody write a good article about why pushing gravity causes gravity. So I was a young kid, and so I wrote, and I entered the competition. He said he was going to give 1,000 points. course, each point was worth a dime. I didn't know that at the time, but it was $100. And I won the thing. So I came in first place, and the guy who was running it was a guy named Bill Carnahan. And Bill Carnahan lived in down where the University of Texas is in, I have trouble with words in my old age, but Austin, Texas. So he flew me down from St. Louis. I was working there at St. Louis at the time. He picked me up at the airport and took me over to the motel, and then I had dinner with him. And I gave it a little talk to the Austin Austin Amateur Astronomer Society out at the Austin Country Club. And Carnahan, he called himself the APG, the gravity pushing research. Yeah, AGPG, the Association for Pushing Gravity Research, APGR. And so then later on, he published a little bulletin, and he asked me if I would be the president of the APGR. It's just an honorable thing. He was going to run everything in the background. So I says, okay, that's fine with me. I was a young kid at the time. It was in the 1960s, I guess. And so here I was the president of the APGR, and the APGR, some old coots, old like me, decided to have a convention at the Golden West Community College in Huntington Beach, California. So they held a little convention there, and I went to it. And Carnahan couldn't show up because he was getting sick or something, I guess, and I think he eventually passed away. And so I introduced the society as being the honorary president, but I was really pretty busy, and I didn't really want to spend much time with the APGR. And John Chappell showed up, and he grabbed me by the arm, and he started telling me, he says, boy, this is really, we need to have dissidents have a chance to say something. We need to form a society. And I didn't really want to do that. And I said, John, you can do this yourself if you want to. So John took it off and ran it. He was living out in California, I think near Santa Barbara, I think, somewhere, San Luis Obispo, I guess it was. And he wound up, he got a hold of the physics professor at Fort Collins, Colorado State University, and they held a meeting of the regional meeting of the American Physical Society, and he had we got a session associated with that, and we had a meeting up in Fort Collins. And so the APGR had a session up in Fort Collins associated with the regional meeting of the American Physical Society. And we had a fairly good attendance. So Home Army, I think, showed up from Canada. And
so what's the bottom line here, John?
And then
we probably
we had another meeting in Arizona at Flagstaff, and I got to that. And then we had another meeting at the University of Connecticut, and by this time he could call it the Natural Philosophy Society. And I had Halton Arp show up there too. I got Halton Arp to show up for that. So way back, the roots of this go all the way back to the APGR, the Association for Pushing Gravity Research, that Bill Carnahan made from Austin, Texas, and it blossomed into the existing society today. Thought you might find that interesting.
We've got some questions for you. So
sure.
Ian's got some questions for you.
Good.
Go ahead, Ian.
Thank you. Well, I think the exposition was quite interesting. Thank you very much for it. In particular, your emphasis that Hubble, despite his reputation, was not an advocate, basically, of the Doppler origin of the redshift. But I've just one or two points which occurred to me as you were speaking. One was when you were analyzing the ordinary tired light explanation, you, I think, took a sort of a linear relationship between distance and energy. Now, there could be other relationships. For example, I've looked at exponential decay, and I think if you put something like that in, you would actually get a black sky, hence resolution of Olbers Paradox. Right. The other thing, just while I have it, is related, is that when you, I'm looking at maybe similar to you, I suppose, in some ways, but a dissipation in space. But I'm looking at a dissipation in the ether because of its properties, its conductivity property, if you like. Now, if you take it to be merely electrons in outer space, well, surely empirically we wouldn't have enough electrons in a cubic meter of outer space to result in that.
Well, it obviously that's a tough problem, because you can show in quasars that they have a concentration of electrons around them. What's interesting about quasars is they have a lot of them have jets shooting out of them at a pretty high velocity, and you can see that the redshift is greater through the jets. Anyway, there is a correlation, but that's why we made the correlation on the sun with the number of electrons on the sun from the center to the edge, and showed that agreed with that redshift. But it's hard to tell how many electrons there are out there. It's, they don't have a spectral range where you can say, hey, if they don't absorb, they bounce off a Compton effect instead of absorbing, like which would produce a spectral line, a dark line, or emit as a bright line. So it's very hard you can play with that parameter as much as you want. You can make it be whatever you want. That's what's real. I'm coming along with I kind of like Viget's idea that perhaps a photon actually does have a tiny mass. It helps solve not only the problem of the Gedanken experiment, and the problem of there's quite obviously gravitational lensing occurring, and it also helps solve the problem of Schrödinger's problem of where you can say the photon goes through the slit where the mass is, not just randomly associated. So there's anyway. Hopefully I answered your question. I don't know.
Well, I had a little comment on does photons have a mass? And now, me personally, I think a photon is strictly a wave phenomenon. So that's why, photon doesn't have mass. But what does have mass is whatever medium the wave is traveling through. So, for example, if you have a wave traveling in water, it's like the wave itself has no mass, but the water itself does have mass, and the water itself can push against things like ships and cause actual forces. So my comment here is I would suggest that the photon itself still doesn't have any mass, but that the medium has a mass. So that would be evidence. I'm also an etherist, so I believe that empty space is not empty. It's actually filled with mass. and that when the photon goes through, that photon causes the matter to collide against, whatever happens to be in space. So I think that is probably the mechanism by which photons can exert forces.
Well, yeah, of course, there's two ways of looking at the interaction of light with a column of electrons, for example. There's the Compton effect, which is proven and Compton got the Nobel Prize for. And the other one is the Thomson effect. And the Thomson effect is that it assumes that the photon is absorbed by the material, by the electron. The electron vibrates in resonance with the photon and issues a new wave just from its motion in reaction to the electromagnetic waveform. And the Compton effect proved to win that bet, that the light acts more like billiard balls bouncing off of each other than it does like the Thomson effect. They still teach both things in physics today, but it's not, it's very, very interesting. The more you get to shorter and shorter wavelengths, the more and more the photon acts like a particle in a way. And that's what's interesting is that Compton was measuring the Compton effect using Crookes tubes, which are like that Crookes radiometer sort of thing, but as just a evacuated tube. And that's how he measured the cosmic rays all around the world. And he did not look at the scattered photons like they were light waves. He looked at them like they were particles. So he saw the way the energy was going. He didn't look at where the E cross H vector was pointing. So there's the big problem that everybody points to with my idea that the redshift is caused by the Compton effect is that people say, hey, that has to produce blurring and has to produce scattering, and the light would scatter all over the place and wouldn't reconstruct. But obviously, light going through a transparent medium has you can see it obviously where it's going. What you see is the E cross H vector, and you don't see the energy in it. And so it's hard to say whether or not, from Compton's experiments, whether the light would reconstruct into a new wavefront or not. There's big difference. I mean, I agree with you that, light can definitely be explained as a vibrating electromagnetic vectors. Like that's what they teach in physics all the time. So it works good.
Okay, so do other people have some questions? If you have some questions, wave your hand in the live room or put a private chat so I know that you want to speak. Or if you've been added to the live stream already, just go ahead and chime up there. So but we do have quite a few other people here who are here today. But I think, I do have some questions about, well, there's some things I like. So I like this idea that the Compton effect can be used to explain the redshift. And so I think that's interesting. I think I would be more in agreement with, Hubble's idea that it is a new phenomenon, right? Because I think that it is easier to believe that there is some physical phenomenon which causes a redshift according to distance, rather than the alternative, which mainstream has adopted, which is that things are speeding away from us. I think that is a harder pill to swallow than to come up with a new physical kind of action that maybe we don't understand, I think. And I think I like the idea that the actual effects are being caused by like radio waves or electromagnetic actions, actually. Rather than what standard pushing gravity is saying is that there's the ultramundane particles, which are coming. I mean, it has to be actually some physical particle, which is coming, raining down from someplace, traveling some distance, and then hitting the thing that's being affected by gravity. Whereas if you think that it's an electromagnetic interaction, then we don't have to have the particles traveling all the way from, say, the sun all the way to the earth. The only thing that has to travel from the sun to the earth is just the wave energy, right? That's the only thing that has to travel.
Well, the gravitational force is the shadow cast by the mass in the background radiation, just like Reber's pictures that showed dark spots where the galaxies are, and that it's absorbing the light. So it's the shadow cast that he's actually looking at the gravitational map of the galaxies when he sees those empty spots in the sky where everybody else sees bright spots at shorter wavelengths.
Let's see, Ray, you just put in a comment here about Paul and Louis Marmot.
Marmé.
Yeah,
Marmé. Yeah.
That
Both of them have Paul Marmé. I don't know if you Paul Marmé is deceased, but he was a very famous Canadian physicist, and Louis, his son. And Paul Marmé has a website, I think it's newtonphysics.com, and he basically explains redshift and pretty much all the so-called relativistic phenomena in a classical way. And his redshift explanation did deal with a Compton effect. His son, Louis, questioned that, thinking that the space wasn't dense enough for the Compton effect to be an explanation, and he had a spectral explanation dedicated, but it's an interesting read. It might make for an interesting relation sometime. I mean, I can send the I can send the links for both of them if someone's interested.
Yeah, I have them already connected to my website. So.
Okay. Yeah. Have you seen Louis Marmé's explanation?
Yeah, I think so. Yes. Paul Marmé at the meeting, he gave a really good presentation of some K stars that were in orbit about each other, and you could map them out, but one had a redshift and the other didn't. So the pattern was separated from the two, and obviously that proves that there definitely are cases where there must be intrinsic redshifts. People just don't believe that there can be an intrinsic redshift for some reason. They don't like it, and the fact that there's redshifts in the solar flares, I think, is really remarkable. But I kind of did a little bit of work on the RHESI satellite and at Spectrum Astro in Phoenix, and these guys are trying to say, oh, well, it must be falling back into the sun at real high velocities, even though it's in the middle of a solar flare that's throwing stuff out of the sun. It's just an intrinsic, in my mind, an intrinsic redshift, a Compton effect redshift. I like Paul Marmé's stuff. And Paul was actually quite friendly with me. I met him in a couple of the APGR meetings and Chappelle meetings, I guess, earlier, and both in Flagstaff and in Fort Collins. So.
not all at once, right?
Sorry, Franklin, just quickly, another follow-on. Has John done any work on looking at the relationship, according to his theory, between redshift and distance? I mean, accurate measurements basically show that the relationship isn't exactly linear. it's approximately linear over short distances. And hence the postulation of things like dark energy has been made to account for things like that. So I'm just wondering, what is the relationship according to his own analysis?
Well, it's an accelerating redshift. It's quite close to linear for nearby sources, but it accelerates as time goes on. I have a link to the paper that I have on my website that you can look at, and I show what their total relationship is. So it's basically just show, and obviously they have been measuring some acceleration in the redshift. They think that they think it's related to the way the universe evolved, but
I think it's like an exploding.
I was a little bit worried there for a while when I do a lot of spacecraft stuff. I worked on Skylab, and I was in charge of all the astronomy and space science instruments on that, and so I've been talking a lot to the scientific community. And there's what was I going to say? It escaped my mind. I'm getting too old. Sorry.
I think Jim Martson had a question here. Jim, if you want to go to your next question.
Yeah.
Hi,
do
Jim.
you know Peter Beckman or Howard Hayden?
I'm sorry, who?
Peter Beckman?
I don't believe so.
Howard Hayden?
Don't think so, no. Sorry.
So who are those guys?
Well, Peter Beckman wrote Einstein plus 2. He has the local ether theory. And Howard Hayden was a supporter of that theory. He's a professor at UConn, and I don't know if he attended any of the John Chappell meetings when they were at.
How do you think the local ether theory works into this discussion?
Yeah,
well, I
when
was just wondering.
showed up at UConn, it was a real. He was a king. He was the king of the show. Everybody jumped on him.
Who?
Holton Harp, Chip Harp. He came over from Germany to for a reunion of his prep school, and he stopped by at the BGR meeting, and everybody just they just love him.
Do you accept the thesis, by the way, that he was driven out of the United States by Hubble?
What about?
Well, it's sometimes said that Hubble was angered at his unorthodox interpretations, and he basically ruined his career and ran him out of the States and forced him to take a job in Germany. I've heard that.
I don't believe it was Hubble that did that, but it was the big bangers all over the place. I think the Chandrasekhars and all those guys who run the American Astronomical, all the people who run the publications. It was really funny when I published that article in Solar Physics. They made me take off the data that really showed the variation between the center and the edge. They made me take off all of the data that was higher than what was predicted by the gravitational redshift interpretation of it. And you're just fighting the wall. And poor Margaret Burbidge. Margaret Burbidge, for even though she was president of the AAAS and president of the AAS, she would send papers in showing that quasars had big red shifts that were attached or associated with galaxies of a lower redshift, and they said, "Oh, Margaret, we can't publish that." She had all kinds of trouble with them if she didn't go along with the Big Bang philosophy. So it's a tough thing to fight. We were lucky to get that published. So indeed, ARP was kicked out of the United States because he didn't believe in the Big Bang, because he was showing objects with two different redshifts that were physically connected together, and which would not agree with the Big Bang. It wasn't really Hubble. It just didn't agree with Hubble's law, is what they were saying, or what they thought Hubble's law was. Hubble himself, he wrote the book called Observational Approach to Cosmology, which was a series of 10 lectures that he gave in England at Cambridge, I believe it was. And in that, he clearly states, without a doubt, that the redshift is not Doppler. And his very first paper that he published, he had to put a footnote on it because he couldn't get it published without saying it was Doppler. He said, in the footnote, it said, "We are so sorry, it's not at all sure that the redshift we're observed is Doppler, but we express it in terms of velocity for convenience," is what he said. Because that's what he got forced into by the referees. It's just...
Yeah, I think the interpretation that perhaps I was referring to earlier is that despite what you say, that's very true in his early career, but he gleaned a reputation for this law, which was the basis which became the basis of modern cosmology, and in particular the Big Bang and so on. And that the contention, therefore, is that he was hesitant to contradict that. I mean, he was happy to bask on maybe a slightly spurious reputation, and he didn't want to contradict Einstein, or he didn't want to contradict the mainstream. So I think that's basically the basis of what I was saying and what I've read. I don't know if it's exactly true or not. There might be something in it.
Well, people took Hubble's law to, as gospel. But Hubble himself, Grote Reber went and visited Hubble when Hubble was getting to be pretty old, and all he wanted to talk about was Reber's mother. He didn't want to talk about the redshift, because Reber definitely did not believe that the redshift was due to the Doppler effect. And poor Halton Arp, he did get kicked out. He wound up taking a lot of my ideas and putting them in. I have this this YouTube video that I made back in 1981, and I sent a copy of it to Chip, and Chip actually used some of that in some of his later. If you look at his last YouTube video that he made, you'll see that it incorporates a lot of the stuff that's in my YouTube video. It's sort of interesting that he was coming around to me. What's very interesting is it's not at all different. I mean, the idea that it's really long wavelength stuff and it's a push is not at all different from what today's astronomer, today's gravity people think about, because they think the gravity travels at the speed of light. There was a big controversy for a long time whether gravity was instantaneous or not, or whether it was traveled at the speed of light. And I think they proved that it travels at the speed of light. And that's what with the LIGO tests that they've done, with their measure, what they're thinking is a big gravitational event, and then seeing how fast it travels between two different sources. They're widely separated. And so it's very interesting stuff. Now, the interesting thing about this if the redshift is Compton, that means and I don't think that it's an instantaneous effect. I don't think it's in the real short wavelength stuff. The photon is so short, it bangs into something and it really acts like billiard balls bouncing off of each other. But when the wavelength is longer, it takes a period of time for that whole wave to pass across an electron or any other particle. And during that time, it's transferring energy. It's not instantaneous. It transfers energy to the particle, the photon or the neutrino or whatever it is that has a small mass. And the smaller the mass, the more energy it receives, it turns out. Then what happens is at the same time, during that time of the light is getting energy, it wants to make the the particle, the photon, or the electron, I mean, go in the direction of being hit the same direction as, to the billiard ball type direction. It's also getting energy, getting a lot of energy in all wavelengths, radio wavelengths to shorter wavelengths from the opposite direction. And the particle sits there and it receives energy from all directions, and it vectorially cancels so that the particle is receiving energy without an increase in velocity, which means it has to increase in mass according to E equals mc squared. And I do know, I've worked at Ball Aerospace for several years, and I do know Ball Aerospace has very sensitive detectors. They're able to actually physically count photons. But when they count the photons, it would be very interesting to see if those photons are heavier. If Viget is right, then the ones, if the old photons are heavier than new photons because they've been hit all the time, and the mass would be increasing. If there really is a mass of a photon, I don't know whether.
Well, I don't have.
I don't know whether all the data is in yet or not to really believe that Viget is right. But it's very hard for my theory to explain gravitational lensing if the photon does not have a small mass. So that's one reason why I'm leaning towards Viget's idea. So
I contend that a photon would have a rest mass, which is easily calculable. It's not actually dismissible even. It's a calculated value. But that's the theoretical rest mass. I mean, the mass, if you like, is theoretically zero when it's traveling at the speed of light. But getting back to your point about instantaneous interaction, I would accept that it's unconscionable because things blow up mathematically where you have instantaneous infinite speeds or you're dividing by zero. But with regard to gravity, the speed of gravity, which you mentioned, I think one needs to make a distinction between the speed of gravity waves, which are waves in the ether, if you like, which are generated by gravitational fields or variation in gravitational fields, and the speed of interaction of those fields itself. Now, the former probably does travel at the speed of light, or approximately speed of light, because they're etheric, if I may use that expression, etheric disturbances. But the latter certainly don't. I mean, both theoretically and experimentally, we've done work, most recently by somebody like Tom van Flandern. He's deceased now, but it actually goes back to the speed of gravitational interaction is something like 10 to the power of 8 times the speed of light.
Yeah, he believed it was very high, almost instantaneous. Maybe I should have said almost instantaneous, not instantaneous. He was the guy who was really promoting that. But the LIGAR people obviously think that it travels at the speed of light, and gravitational waves are. So, as you say, you have to make the distinction.
My contention is that they, in the LIGO experiment, are confounding the speed of gravitational waves generated by variation in gravitational fields with the speed of the fields themselves. They don't understand the difference, or they don't want to understand the difference. I'm just being a bit contentious now, but I don't say they just disagree with Van Flandern. I said they fundamentally misunderstand it.
Uh-huh. Well, the idea of gravitational lensing is very interesting because, it's obvious that that occurs. I was kind of doubting it for a long time. I thought it was just normal light traveling through just normal lensing effects from light passing nearby an object that had a big atmosphere about it, and so that would cause the lensing. But I have to come around and say I think the evidence is becoming overwhelming that there really is gravitational lensing, and it's not just the effect of gravity causing big atmospheres that the light travels through. to cause lensing. So it's still possibly that, but I'm not sure. Go.
Well, Kenneth Morris here, he's got a comment here saying that the gravitational transverse redshift caused by an effect similar to the maximum stellar aberration of a transverse star. I'm not exactly sure what that means, but there's some idea about a transverse redshift. Although, you know, redshift just changes the frequency of the light. It doesn't actually bend the light.
Right.
In order to bend the light, you have to have like something like a lens, which has a different refractive index around it. Typically, that's how, you know, optical lenses work. I personally thought that gravitational lensing is actually a refractive change because gravity must compress the space around these objects and change its refractive index, is what I would think. But I had just another comment about the Compton thing, which is that I think they should just try and directly measure the redshift directly, actually, because it's kind of just speculative as to whether what's causing that thing. I think we have spaceships which are far enough away, like the Pioneer and Viking spacecraft, that maybe there's enough distance there that we could directly try and measure any redshift of the signals that are being transmitted to the Earth. And I know there's some, like, you know, weird redshift, blue shift things going on, but I don't know whether that's that, or come up with an Earth-based or maybe Earth to Moon based experiment to see whether we can see any of that frequency shift through just space. And if we can just observe that, then we can probably even dispense with, you know, what the cause is and just accept that space has this property that it will redshift light. But that's what I'm looking for. I'm looking for a direct.
There are the only cases where you could really see that sort of thing, because it's such a minute thing, is when if the star is all occulted by the sun and it travels through the sun's atmosphere, it should have a bigger redshift from going through the sun's atmosphere than if it's hitting the electrons there. Unfortunately, there's so much noise put out by the sun that it's really hard to track the signal to see whether the signal actually tracks it. There's been a few people who thought maybe the Pioneer, not the Pioneer, but yeah, maybe it was the Pioneer satellites. A couple of them that were occulted by the sun. They did see the signal shift frequency, which would have been a Compton effect shift. But anyway, it's still up in the air there, whether it's not conclusive.
Yeah, I just like to see an attempt to make a direct measurement, just to see, you know, without any sun, without just blank vacuum space, can that shift the signal, a radio signal? But I had to bring up another point, which is that these kind of pushing gravity theories, you know, they kind of presume like a Mach's principle that basically the force is coming from the outside of you, like from the universe, basically. But, you know, I can point to experiments where they just take like 2 lead balls, like the Cavendish experiment, and you can fairly accurately measure the same force of gravity between even these 2 small little balls that we have on Earth. Now, because we can do that, I can almost presume that if I were to remove the entire universe around these 2 balls, that they would still show gravitational traction, which would kind of point out that gravity, I mean, intuitively, most people think gravity is a property inherent to the object. And in that, usually you think gravity is being created by the object. So if I have a lead ball, we normally think that the gravity is coming out of that ball, right? As opposed to the pushing gravity people who feel that gravity is like a Mach's principle thing. Which
right. Right. Understand.
So I'm explaining the Cavendish experiments where we can measure gravity off of these very, very small masses. And it looks like the gravity is actually coming out of the masses. It's not having to do with anything on the outside.
Well, you can't shield it from going from the outside. I don't know how you would do that experiment by preventing it from seeing the outside.
We can't. That would just be a thought experiment. That if we were to do that,
yeah,
if you repeat that experiment, and if the pushing gravity people are correct, then you should not measure any force of gravity around those two balls. Right. Or if you don't believe that, if you believe that gravity is coming from the two balls, then it shouldn't matter that you remove the entire universe. The gravity would still be there. And I think that it's easy to understand pushing gravity when you think about things like the Earth and the Moon and shadowing, but I don't see how that works when you have like two balls in front of you. I mean, what's shadowing what, right? And what is it being shadowed from?
The standard theory is that gravity is a warping of space. And so they think there's space there that is warped by these two balls. And whether the rest of the universe is there or not, you could still see that warp. I think you got to have the rest of the universe there. I mean, I believe in Mach's principle that defines an inertial system as a gravitational system is it has to be, it's that's the way it has to be. Otherwise, you'd have a geosynchronous satellites would come crashing down into the Earth if you took away the external. If you
well, why would that be? I mean, I don't think that follows.
If you choose your reference system to be the center of the Earth as your origin, and the reference system is spinning with respect to the ball, and you take the rest of the universe away, the geosynchronous satellite should come crashing down in. But Mach's principle says, hey, that's not an inertial gravitation. That's not an inertial system. You can't apply gravity laws to that. It has to be an inertial system. And Mach says, well, wait a minute, to be an inertial system, you really got to have the fixed stars out there moving around. If the rest of the universe isn't there, then gravity disappears. Or, I mean, you can't apply Newton's laws. So
no, that doesn't follow at all.
That's the way. Well, if you chose that reference system right there and you took the rest of the universe away, it would come crashing down.
You could easily pick the Earth-centered inertial frame, which some people like because experiments tend to seem to think that that's a perfectly good frame. And then you have your geosynchronous satellite, which can be said to be heading at X miles an hour around that point, and then you can work out the whole gravity versus centripetal force thing. And so I just don't see how removal of the universe has anything to do with that. It's just I just don't understand.
Well, if your coordinate system is moving with respect to if the two objects are not moving in that coordinate system because they're both rotating.
Yeah. Pick a very special coordinate.
Over r squared, it ought to come crashing down. But it doesn't come crashing down because it's not an inertial coordinate system. There's Coriolis forces and all that sort of stuff going on that have to do with the spin of the Earth, and because it's not an inertial coordinate system.
So I'm not quite sure you've answered my question about like how the Cavendish experiment works, right? With two very small masses, right? How does that work? You'd think that the vast majority of the gravity force should be coming from the outside world, but it would seem that and it would be coming in the wrong direction. Actually, I would think that if the vast majority of the gravitational force is in fact coming from the outside universe pressing down upon the Earth, then really there shouldn't be any force between two adjacent objects at all. The only force, all the force would be heading straight down towards the center of the Earth only, right?
Yeah.
How do you respond to those kind of arguments?
So you're saying the geosynchronous satellite should come crashing down?
No, I'm saying that I'm talking about Cavendish experiment. You've got two balls sitting on the Earth, and I'm saying that according to the pushing gravity theory, the vast majority of force should be coming straight down. Right? There really shouldn't be any force between those two.
I don't believe there's any difference between Newton's laws and the pushing gravity, or whether it's a pulling gravity.
That's not answering the question. It's like, if you have a hypothesis, and the hypothesis should make specific predictions, and this is a prediction that I see as not coming true, because I still feel that the Cavendish experiment is much more in favor of saying that gravity is coming from the mass itself. That we can have these two little balls on the Earth.
Well, that's a characteristic of the mass, is that's how much how big a shadow it makes. The bigger the mass, the bigger the shadow. And so if you take away the shadow, the Cavendish experiment, we were going to, unfortunately, we didn't do it. We were going to try to do the Cavendish experiment on Skylab. And unfortunately, Skylab had too much vibration on it that we couldn't make it work. But
well, that's interesting. What were you trying to measure? What were you hoping to see?
Well, it was a high school experiment. One of the high school kids had proposed an experiment, and we tried to figure out if we could do it or not. And unfortunately, we weren't able to do it. But they were going to put two balls and try to measure in 0G in orbit around the world, and try to see if they could measure the gravitational attraction between the two balls that are both while they were in a 0G environment. Unfortunately, we didn't have a decent enough 0G environment to be able to make those kind of measurements. It would have been a very fun thing to have tried. Maybe we could might be doable nowadays. I don't know.
Maybe. I mean, I would think that orbiting spacecraft would probably be the lowest vibration environment you could probably imagine.
Well, unfortunately, a manned spacecraft is tough. It should be done in an unmanned place where you got all kinds of stuff going on with, in order to keep the people alive that cause vibrations and stuff. And it was just, unfortunately, just too bad. But there's another set of experiments that were done that we had two satellites following each other in orbit, one right behind the other. But what we were doing there was we were mapping the gravitational field of the Earth, because as one hit a mass con, we call it, or a mass concentration on the Earth, the satellite would speed up, and so it would get ahead of the one that's trailing right behind it. So the distance between them would move back and forth. But what we were mapping was not really the attraction between the two satellites. It was the actual gravitational forces on the Earth, the Earth's gravity. So, and on the Moon is really clumpy. It's got lots and lots of mass cons, and the Apollo satellites sped up and slowed down and went around the Moon several times. So it was really very interesting. But that's beside the point. I mean, that doesn't prove whether it's a push or a pull. So.
Well, I'm thinking that generally speaking, all forces actually have to be a push, because I don't think nature has any inherent way from Newton's laws to create an attraction. Like if you have two billiard balls on a table, if they're moving together, it's because something bumped on the outside of them to cause them to move together. There's nothing in Newton's law that says that one particle will just spontaneously move towards another particle. So in that way, I agree that, push gravity has to be a kind of push, because it's really the only force that's generally available to nature. So like everything that looks like attraction, even like an electron and a proton coming together, must in some way be a push.
I think I need to sign you up.
But like I said, I like the idea that the push comes from an electromagnetic wave, because that means that we don't have this problem about having to deal with the energy of the particle actually being deposited on the Earth. That's the other problem with the pushing thing, that if it was a particle, then the Earth would burn up in like 5 seconds due to, say, all the particles coming. But if it's just the electromagnetic wave going back and forth, then it's not depositing any permanent amount of energy onto the thing that's receiving the energy. So I like that, but I still like the idea that that the gravity itself is actually a property of the material itself and not coming from the outside world. So
that's why I was stumbling through that business of trying to calculate the solution to Olbers Paradox. And that is that depending on the nature of the redshift, you can determine whether or not there is all this radiation coming out there if the universe is infinite. Now, and that's, you got to go do the infinite series and say, hey, you know, from here to here, plus here to here, plus here to here, plus here to here, you can see that the amount of energy that's being given off, if it's all been redshifted, then there's a whole lot of it out there in the real long wavelengths. But if it's a Doppler effect, there isn't a whole lot out there because of the time dilation. So the radiation is there to cause gravity if the universe is infinite and if the redshift is, if the universe is not expanding. And if so, and if there's a conversion of energy from mass to electromagnetic and electromagnetic back to mass again.
well, like I said, I would.
You got to think of infinity. That's why you have to think about eternities. That's why I call that the eternity website.
I would disagree with, say, the idea that is coming from the outside, because like the intuition is that the gravity comes from within the object. So if I have 1 kilogram mass and I remove the rest of the universe and I put it next to another 1 kilogram mass, I would feel that those two would still attract each other, because I don't believe that the force is coming from the outside. Now, I believe that because I'll just tell you a little bit my own personal gravity theory by comparison. And I feel that gravity is actually an inherent property of the material itself.
Well, it is because the material itself casts a shadow, and in the background,
casts a shadow.
You can quantize the gravitation. You can look at it as being inherent in itself, and you can have a graviton, but the graviton in this case is a quantization of instead of being like a photon, being the quantization of the light going out there, it's a quantization of the shadow in the photons around there. So there is a way of looking at it. It's just like flipping it, looking at it in the negative, instead a negative picture instead of a positive picture. So,
well, you can always do that. But I just got to tell you,
I agree with you that the mass is inherent in the object, because in my mind, the mass is what the size of the shadow cast. But you say it's somehow or other something that's going out and grabbing things and pulling them together, and I say it's being pushed together.
Yeah, well, we can all say those things, but I would say that gravity is coming out from the object, and I think that gravity is, for example, just an electromagnetic emission from the object. Like I said, electromagnetic.
It's a weaker emission.
Things around. So if if you have the object and it's like has a net charge of some sort, then that will radiate out something like that. See, I think the gravity is more like that. Gravity is more like something that radiates out from the object as if you had a charge. And that's how I actually see it. Right. Like the Earth is just a big positive charged object, and that attracts all neutral matter to it, and that would also be an explanation for how gravity works.
Well,
But has some elements.
That's a good explanation, but and it's a good description of what of it. But the description and the mechanism are different. I believe exactly what you say, except it's the shadow that casts by the mass that comes out. It's just exactly the same way you do it, but it's the external radiation from the outside given off by radiating forces of the rest of the universe that makes it there. No.
Once again,
So,
between
it's
different
not
theories,
that much. It's just a matter of whether you're using a plus sign or a negative sign.
well, I think it goes more than that. But it's like I can't perform my experiment. I can't remove the entire universe and then show that gravity still exists, right? Because we have no way of doing that, right? But if I could, then we might have some way of telling the difference between the various theories, right?
Right.
But there are, but that's what we do here. We discuss various possible theories, and it's it's very hard to tell whether what we're talking about is just some kind of fairy tale or has any actual empirical support.
Well,
since we can't, perform, experiments, like we can say things theoretically, or we don't have enough money to actually perform the experiment itself. But that's why we sit here and debate. That's what we do.
Right.
But
well,
looks like
your idea is basically saying that, hey, there's that you don't need to have the rest of the universe there to have gravity, and Mach says you have to have the rest of the universe there to have gravity, and so that's just the difference between Mach says there's something physical that's associated with an inertial reference system where gravity works, and Newton said, I was just thinking of these things, and the rest of the universe didn't enter into it at all. So you're on Newton's side, and Mach is on his side, and
yes, and we shall continue.
I like Mach.
I like Newton. I'm a Newtonist.
Well, I like Newton and I like Mach both.
I like to explain everything.
Newton was well aware of the pushing. Newton was well aware of the pushing gravity theories because his assistant was Fabio was a big proponent of it, but he wouldn't embrace it. So he's with you. You've got good standing there. So.
Yeah, it's like the ongoing debate here. That's what we debate.
Yep.
So you make fun of my theory, I'll make fun of yours. Okay.
I'm not making fun. I was just telling you the difference.
Okay, but I think we've come towards the end of our discussion here.
Good.
So I thank John for coming today and presenting his stuff. So I do believe we do have at least a link I can leave everybody here. Let's see here. So if you want to find out more about John's stuff, here's a banner to his website here. So, but that deals primarily with the Big Bang Theory being wrong. What we heard about today is more like gravity. The relationship between gravity and the redshift, or actually the source of the redshift.
Right.
And I think that was very interesting and important that you may have attributed the redshift to, say, the Compton effect. Although I think it may be valid that since the Compton is a scattering effect, that the redirected photons would kind of be blurry. Although maybe it doesn't, because it just has to do something with the wavelength losing energy to something that's present, like the electrons. So, I mean, I could certainly believe that. I would find it harder to believe that light can travel, a billion light years and not be affected at all, right? That means not losing any energy at all after traveling a billion years. And I find that to be harder to believe than the light does lose some energy. And if it does, how can light lose energy? It can only do so by redshifting, right? So if it lost any energy at all, it would have to redshift. At least that's kind of how the way I see it. So
sounds good.
It may or may not be due to the Compton, but it looks good that, you can see these effects. I think that's the best explanation of why a quasar have this multiple redshifting. That's not the same as the galaxies, because it's an inherent effect around the quasars, right? So
Right.
I think that's very important.
Good.
And but that was the discussion today. So that will do it for this week. And we did not mention the COVID virus, not even once today. So everyone stay safe, and hopefully see you here next week then. Thank you.
Thank you. Appreciate it.